the primary effluent flow is going to enter the basins. This is the aeration train. It's going to enter through where I'm standing, and then it's going to flow along through this channel under my feet down to the end of where those people are standing over there, and then it's going to go down in that channel underneath their feet all the way to the far end of the basin, and then that's where it's going to enter the aeration basin. And the basin that you're looking at right now is train 4. It's the western side of the plant. The primary effluent, it entered down in that section of the tank and goes along the channel that they're standing on right there all the way to that corner, and that's where the primary effluent enters the aeration basin. This is train 4, like I mentioned before. The flow then travels along through here, through an anoxic zone, through these 2 channels right here, and then it's going to go down to the around underneath this catwalk out that way where we aerate it, these are oxic zones. These valves right here are really important. These are air lines which feed air to the parks and air panels that we use here at the plant. We have DO probes in the basins that are measuring the DO throughout the basin, and then feeding that signal back to the SCADA system, which controls these valves. So we're able to, through the SCADA system, maintain a constant DO at the various locations in the aeration basin. And this is the valve that regulates this section of the basin right here. We can enter set points on the computer, which will control the valve based on DO when it's in auto, or if you select through the SCADA system, you can also select manual and open and close this valve manually. But under normal operations, this is in auto. I think what's important to remember about this valve is that this is a pneumatic valve. It uses plant air. If you ever have a power outage or something like that here at the plant, one of the things you have to watch for is the Ingersoll Rand air compressors over in Power Center 2. When they're not running, we're not producing plant air, and the lack of air will cause these valves to close. So getting the Ingersoll Rand air compressor up and running is really important to get air back into the aeration basins. So in a power outage, a couple things you want to do is make sure that these valves are operating correctly, and that means they have to have air fed to them and that the blowers are restarted. Because with a combination of the blowers producing the air and these valves being open allows us to aerate the mixed liquor. And then what we have right here, this is a local indicator for the airflow into this particular section of the aeration basin. Right here, these are anoxic zones, and you'll see the airflow is 0. Over here on the oxic zones where we're feeding air, you can read the air right here at 1642 SCFM. And that is measuring airflow through this pipe right here, which is feeding air to a network of pipes which feed our diffused air panels. And over here, you can see the air is coming through this line right here, and it's feeding this header right here. This is one of the headers that feed our air panels, and these valves are each connected up to a network of fine bubble diffusers, and when air is fed through that valve over there to this system, you would see air begin to flow through this basin. What we found here at RP5 is the blowers are very large, and we actually were over aerating. To get our TINs down, we had to drop the DO, so we have huge anoxic zones. So at the flows and the loading that we currently have, we have these air panels isolated. As the flow increases, we'll probably have to bring these panels up online. These panels right here, you'll see these all around the basins. We have anoxic mixers down below, and the purpose of the anoxic mixer is that when we have air panels turned off or it's in an anoxic zone, is to keep the mixed liquor in suspension so that we don't have a lot of settling. And you'll see these throughout the basins. There's like a total of 23 of them spread between the two trains. You can see right here I've got local control, stop, start here, and then the breakers for those are located in Power Center 2. During a power outage, you will lose, in Power Center 2 over there, you'll lose the blowers, you'll lose the air compressor, and you're going to lose all these anoxic mixers. And the best place to go during a power outage is Power Center 2, and I'll show you the breakers in this video, and you can restart all these without having to run around the whole aeration train and restart them. Okay, what we want to do to determine the set points for our aeration system, as we look at our plant effluent data, secondary effluent, final effluent, and what we're trying to do here is reduce our total inorganic nitrogen, trying to get that value as low as we possibly can. And we want to run the least amount of air that we can through the system because one, air costs a lot of money to produce, the blowers are expensive to run, and two, in the absence of oxygen, you can reduce your TIN. So what I'm looking at is our TIN values. When I see TIN rising, what we'll do is begin to trim back on the air. But there's a fine balance. If in the absence of air you have organisms like this, Nocardia foam, see, it's a trade-off. You want to get your TIN down, you're going to run a lot less oxygen, but then you're going to risk having foam up on these basins like this. But to answer your question, how we set the air here is based on our TIN values. These gates right here are allowing the mixed liquor to exit the aeration. This is train 4. To exit from train 4, they're going to flow into this channel right here and then off to the 4 secondary clarifiers. Right now we only have 2 online because of the low flows. If we wanted to take train number 4 offline for maintenance, what we would do is shut these 3 gates. The purple piping around the perimeter of the tank, this is utility water, and we use it for foam control. These are little spray nozzles that are all around the perimeter of the tank, and we use that to kind of move foam out of the tank. And each one of the nozzles has a little valve on it to where you can adjust the flow or shut them, turn them off or on. And then I'll show you down below where you can turn the entire system off or on. These units right here are the DO probes. This is the output for the DO probes. And you can read the DO locally here, or else you can go to the SCADA system and take a look at the DO. Each tank has 4 probes in it. The signal from this probe is fed back to the SCADA system, and the SCADA system then will manipulate the air valves over there to increase and decrease the amount of air being fed to each one of these basins. For operators, the only responsibility that they have with this is to, we're taking down the DO every day. We're entering set points into the computer system. Like if we have a set point of 2.0 for an aeration basin, what we'd expect the operator to do is take a look at our set point compared to what we actually have on the system. If we're not meeting the set point, we need to have instrumentation take a look at the probe, make sure that it's a valid reading. These do require periodic calibration, and the instrument techs will handle that. These 2 samplers right here, these are composite samplers that we use. This is train 4 and there's train 3. We use composite samplers to pick up mixed liquor samples. We use the mixed liquor samples for analysis for mixed liquor concentration, and we run a 30-minute set test every day to determine how well what the settability is in the plant, which in turn is used to determine the plant's SVI. And they both just went off. Well, this hoist right here is for removing anoxic mixers, and you can pick it up and move it around the basin. It slips into these pipes right here. And to raise one up, you take the cable which is attached to the anoxic mixer and feed it through the pulleys there, and you can use this hoist to lift it out. And it's important on this system right here to remember that there's about 7 different alarms coming through to the SCADA system through this cable right here. So in addition to providing power to the anoxic mixer, the cable's also got a lot of telemetry, and it's kind of delicate. So when you're pulling an anoxic mixer out, you want to be careful to remember that in addition to just this power cable, which is pretty tough, you have a data cable coming up, and that's not so sturdy. So yeah, you would just latch this onto the hoist and then winch it up. And then each one of the anoxic mixers has a cylinder like that where you can relocate the hoist to. Right there in the corner, that's the primary effluent entering train 3 right there in the corner. And over here, the flow that's coming out of here is the mixed liquor return pumps, which is scalping mixed liquor from the secondaries and putting it back into the head of the tank. The gates here, that's primary effluent. We have the ability, right now we found the most efficient way to treat our flows is by having this gate here on the very end all the way open. But if you wanted to, you can do what they call step feed and have primary effluent enter through that gate over there. There's several gates along this train that you can open up and vary the characteristics of the inflow flow. And the same with the mixed liquor return pumps. There's some gates along this channel that we're standing on. You can open that up, and then instead of having the mixed liquor return to the head of the tank, you can have it return like about halfway down through the tank. As you can see, this basin here has a layer of foam on the top. This is Nocardia foam, and Nocardia is a low DO filament. So it's important to, as you're making your rounds of the plant, to take a look at the basins. The basins will naturally have a little bit of foam on the surface, but typically you'll see something like that, which is just mixed liquor with a little bit of foam floating on the surface. But you can see there's a lot of Nocardia on here. So if you're out making your rounds and you see Nocardia foam on the surface, be sure to log it and let us know that you're seeing foam up on the surface of the tank. I think what we're probably going to have to do, open and close some gates and kind of let it flow into the secondary system. You can see it flowing over the weirs right there. What we're talking about doing is increasing the amount of flow through diversions to push it out to the secondary system. Nocardia is tough to deal with. At RP2, we used to vector it off and take it to the sludge drying beds and let it bake in the sun. You can use water sprays to get rid of it, but basically you're not getting rid of it. You're just helping it along to get out of the system. But it's difficult to deal with. So if it gets started, it's pretty bad, because if you don't deal with it right away, you can have a really big problem. Here, what we did is we raised the DO. What happened here was the blower was in manual, and we lost in manual, the blower it was pumping air into the system, but not enough. And although the valves were in auto, they were 100% open, and we just didn't have enough air flowing into these tanks. And then the Nocardia took hold and grew. With the valves open at 100%, if you're looking at the SCADA system and you see that your set points are not being met, what you want to do is bring up the valve graphic and take a look at the valves. If they're 100% open and you're still not meeting your DO set point, you want to have the instrumentation guys take a look at the DO probe and make sure that the probe's really telling you what's really happening. If the DO probe is right and the valves are 100% open, you want to take a look at the blower and see, is it producing enough air? We should have a set point. The system pressure here at RP5 is 10 psi at the blower, and I'll show you on the SCADA system where you can see that at. And we will increase that. Sometimes we'll go to 10.5. But at 10.5 psi throughout the system, you should be able to achieve adequate DO throughout the whole basin. And the valves at that point, they should not be 100% open. When the valves are 100% open, it's telling you that the blower is pushing out as much air as it can and that it can't meet the DO set point. These blowers are enormous, and they can produce that kind of air unless they're being unless we have put in a command or put a set point in that will allow them will force them not to do that. Under normal circumstances, I think the DO here is like 3,500. When you're coming up to, let's say there's been a power outage or something, and the blowers are first coming on, they're gonna try to bring the DO up from like 0.5 or 0.3, something like 0.3, 0.5 or whatever. You'll see the blower go up to like 10,000 SCFH to bring the DO up. So they have the ability to go quite high, but if the set point is set low, they'll only reach that set point and it may not be enough air. These things are connected to, these are the blowers that are made by Turblex. These are on the Foxborough system. Everything you could imagine is available through the Foxborough through the SCADA system. So if you want to know what the bearing temperatures are, how many amps, how much air, what the system pressure is, it's all available in the Foxborough. If I set this to local, this is the pressure that it's going to operate at. It's going to operate at 10.5 PSI from right here. Occasionally these will get changed. Maybe during a power outage, the default value will be very low. But to start this up, following a power outage, you make sure it's ready for start. Hit that button right there, ready for start. Hit that, it'll bring up this blower start command. Hit that. The blower's gonna go through a pre-start. Basically, it's just gonna check and make sure it's got oil, cooling water, and all that. The blower will check all this stuff. As long as everything is good to go, the blower will start up. But in an emergency or something like that, power failure, if you're the only person here, all I'm doing is going here, ready for start. I hit that, and then I'll go start the air compressors real quick. Because this is going to handle itself. It won't start unless everything is correct. If something did happen though, and you came in here and the blower's making a lot of racket, or there's smoke coming out of it or whatever, this is the E-stop right here. Just go ahead and hit it. If you want to shut a blower down, and it's not an emergency, you would just hit this blower stop command. And this one here, I'll show you on the other blower that's online. That's that. This here, if you bring up a display and it looks like this, you want to just hit main operations. And that display is usually what we have up. But it has another thing, like if the mechanics, if they want to look at things, they can bring up different displays and look at different temperatures and vibrations and things like that. There's a acknowledge for alarms. We don't have any alarms, but if we did, there'd be a page for that. But anyway, to bring up the page that an operator would want to use, it's from menu and main operations. And again, if I want to start it, it'd be right there and bang. I'd push that button. If I want to shut this down right now, I'll hit stop. It won't stop right away. It's going to go through a lot of diagnostics and slowly begin to bring the blower down. These are the hour meters. We want to take the readings on these, and what we want to do is balance the run time between the two blowers to make sure that we just don't run blower one all the time. So we want to make sure we try to rotate these about the first of the month. We'll swap blowers. Right now, blower number one has less hours than two, so we're running it a little bit longer. So from here, these are Ingersoll Rand air compressors. And these are the air compressors we use for the to run air to the filters, the tertiary filters, and they also provide air to the pneumatic valves on the aeration basin. So it's really important if you have a problem here in the plant, particularly a power outage. Some of the first thing you want to do is come in here, start the blower, and then come by here and start this air compressor. If you start a blower up and this air compressor isn't running, the pneumatic valves up on the aeration basin, they won't open. The blower will still run, but you won't be pumping any air out there. Right now, this isn't too bad. But if this tank were covered with, let's say it was covered with foam, and if you look down into this trough right here, and it was full of foam, you would know that there's a problem. You're not pumping with the scum well, the scum pumps over there. And I'll show you something else too along here, is that this is the what they call a ducking skimmer. And it's controlled by the sweep out there. And what the sweep will do is, as it comes around the secondary clarifier, it hits a little whisker switch right there. You can see it just on the surface of the water. When that hits that switch, it will begin to lower the skimmer. I'm doing it manually right now. But what will happen is this skimmer will rotate down and begin to take liquid into the trough. And skim off the surface of the clarifier. One of the problems that you can have though is if the skimmer is it stuck or something like that, or else that's what we've seen the most frequently is the scum pump station is full. Now right now you can tell that there's no problems with the scum removal system because this liquid is flowing. Here right now you can see it's all this is, I'm going to stop it right here. But see how the trough is flowing? If the scum pumps were not doing their job, this would be standing, that would be standing water right there. So that's how you can tell that the scum pumps are having, the scum removal system isn't working. And what I do when I'm out here in the field and I see there's a little bit like a layer of like a film like we have here today, what I'll do is I'll put the ducking skimmer into hand, and then I'll just lower it just a little tiny bit and then stop it just enough to pick up the little bit of film that's on the surface of the water. You can see it flowing over there. And then this isn't too bad. The problem you have here is you are picking up a little bit of Nocardia foam off the aeration basins. It's getting in here. And then as the sweep is turning it's turning just a little bit slow. It doesn't have a chance to get over, you know, basically you're picking up a little bit of debris here between sweeps. And rather than rotate this down and just return a whole lot of water to RP2, which is what we'd be doing if we did it, we just go ahead and let this system handle it. I suppose we could probably look into speeding up the sweep because we are picking up a little bit of debris here on the surface of the water. Normally we'd like to have it looking, you know, perfectly clean. The flow from the secondary clarifiers, or the flow from the aeration basins, comes up through the center of this secondary clarifier, and you can see it being fed up through here. It's hitting this baffle, and then these deflector plates which spread it around through this ring around the outside, which basically it's trapping a lot of foam. There's little ports here which will allow it to be released, you know, onto the surface, but not all at once. It's kind of evenly spreading the mixed liquor around the clarifier. You know, it's like it's coming up through the center, through this center ring right here, and then out through these ports. This is basically a scum baffle too. This unit right here is the drive for the secondary clarifier sweeps. And on the bottom of this tank, you'll have sweeps, and we can actually go look at one of the tanks that's offline. You can see what they look like. So this is secondary clarifier 4A, and it's drained, and you can see the flights. And right up on the top, those are the flights which skim the scum from the surface of the water. And now you can see they're hinged so that as it pushes the scum along, it'll hit the ducking skimmer right here beneath me, and this will rotate down after the flights hit the whisker switch over there. Rotates down, and then the sweep right there will push the scum into the skimmer right here, and then they'll rotate down and flow beneath the skimmer. So that's how we're able to skim the solids off the secondary clarifier. On the bottom, you can see the scrapers, and what they're doing is they're pushing the settling mixed liquor, well, now it's return activated sludge. They push to the center of the clarifier to that trough down there where the RAS pumps can pick it up and then send it back into the aeration basins. And then the flow to the secondary clarifier comes up that center shaft, and that's coming back from the aeration basins underground through a pipeline, and then right up through the center where it's dispersed in the center of this ring over here. And let's see, it's kind of hard to see down in there, but what'll happen is the mixed liquor flowing from the aeration basins will flow up that center column, and then this baffle here will then spread it. It's trying to evenly spread it over the surface of the clarifier. And then this other ring on the outside kind of keeps any like foam or whatever, floating debris kind of trapped in the center ring, and that, out the surface of out in the secondary. This here is the drive for the secondary clarifier, and it does have alarms attached to it. When the drive hits 80, I want to say 80%, it's measured in torque. When it hits the motor hits like 80% torque, you'll get an alarm, like a priority 2 alarm, saying that I'm hit high torque. Then at like 90%, you're going to get high, so it's telling you it really hit something. There's shear pins in here. If it does hit something really solid, it's going to break a shear pin, which will separate the motor from the drive unit and protect the motor from destroying itself. So the shear pin will break. So you get alarms for high torque, shear pin will break. This is pretty important. If the sweep goes down, you're no longer removing sludge from the secondary clarifier, and if it's not caught in time, it can pop to the surface and cause a great deal of problems, because it's going to flow over the weirs and into the filters. So this is something you want to check every day to make sure that the flight is operating properly. And let's see, on the Foxborough system, when this is on, you'll see it. You can't turn this off or on remotely, but it will give you a run indication. When you bring up the secondary clarifier details on the Foxborough system, if this is running, it's going to be red. If it's down, it'll be turning green. So that's really handy when you're like starting up the plant, particularly after a power failure, which is probably the biggest thing that happens here. The most difficult thing to handle is a power failure. You can go through your SCADA screens and see what's running or not. So you should see 2 of these red, which would be clarifier 3B and 4B. There's two pipelines here. One, the purple line, this is utility water. So it provides water to the foam sprayers to break up any foam that's on the surface of the secondary clarifier. Then the other pipeline with the orange handle on it and the yellow color coding, that's bleach solution. And if you wanted to control algae growth on the weirs of the secondary clarifier, you can feed bleach directly in through that line right there to the perimeter of the secondary clarifier, and the bleach will flow over here and then kill off all the algae. So you can see that. And the bleach flows out of those little 90s that are on that pipe. We don't use bleach here for algae control because it's very expensive. What we have been doing is just periodically rotating the secondary clarifiers like we have here, and then we'll just let the sun bake the algae off and then restart the secondary clarifier and then let the other, the dirtier clarifiers bake in the sun. What I'm standing on here, this is really important to understand how this operates. When we want to de-water a clarifier using pumps, because right now when we pull secondary clarifiers down before, we've used the RAS pumps to pump them out. But if you're in a situation where the RAS pump will not pump it out, this structure is where you would do it. All 4 clarifiers are fed into this tank. There's valves down below from each clarifier, and it's a big wet well. So if I wanted to pump this particular clarifier down, after I open the hatches here, I'd go down there, open that valve to this clarifier. This will begin filling with water, and then we can pump it over the wall back maybe to another secondary clarifier or a manhole in the street or something like that. What's really important to remember though is because this is very low and the secondary clarifier is hot, the liquid level is very high, if that valve is left open and you have a clarifier attached to the other end of it and you're filling that clarifier, it will fill this pit and it will overflow onto the ground due to the difference in elevation. This is really, really important. If you're ever taking a secondary clarifier offline and you're using a pump to pump it out and that pump fails, it will overflow into the street. If you're ever putting a secondary clarifier online, this valve has to be shut because you'll begin to fill the secondary clarifier, it will fill up, it'll begin to overflow this pit. So it's really important. And also, the secondary clarifiers are fed from that tank right over there, the aeration basins. So you can see from where I'm standing and see how high that wall is, it's going to be a lot of liquid. So this is very, very important. That in fact, with the contractors, we debated about even just pulling the wheels off these valves. That's how critical that was. That's very, very important to understand how that works. What we're looking at right here, this network of piping is for the RAS pumps, and as the mixed liquor flows out of trains 3 and 4 to the secondary clarifiers, we use RAS pumps to pump it back into the aeration basin, and we do that through these pumps. The discharge of the RAS, it comes up through here. You can see from this arrow right here, and then across the top, and then back down, and that takes it off to, this is train 4. This is the mag meter for the RAS pumps. If you've got a local indicator here, we take totalizer readings every day on it, or if you want to see the instantaneous flow, you can look at it here or on the Foxborough. If we need to service the mag meter or we need to service this pneumatic valve right here, we can bypass flow around it through this top pipe. This pneumatic valve is designed to equalize the RAS flow between trains 3 and 4. You can go with flow equalization on these to where as the flow increases or decreases, the influent flow increases or decreases, this valve will open and close to set your RAS rate proportional to the influent flow. We don't use that. What we have right now is these valves are they're open 100%. On both trains 3 and 4, and we'll probably in the future look at doing that, but right now for this tape anyway, they're just open 100%. This is the RAS pump station right here, and each secondary clarifier has a dedicated RAS pump, 4 clarifiers, and here's the 4 pumps that handle the job. In the event of a problem, if we have to pull maintenance on one of the RAS pumps, we can use RAS pump number 10, which is the one on the end. And you can see it's a little bit different because of the valving and things like that below. The reason that is like that is RAS pump number 10 can be used in place of any of these other RAS pumps by changing the valving down at the base of these pumps. And you can put RAS pump number 10 online. We usually don't run RAS pump 10 only on occasion just to exercise it, because we don't want it to sit there and freeze up or something like that. But it's really important to take good care of RAS pump number 10, because it's the only pump in the RAS station which can replace any of the others, because of the way the piping is. These pumps can be controlled from the SCADA system. You can dial in flow rates through the SCADA, or locally you can go into Power Center 2 over there, and you can put them in manual local, and you can control them with a little potentiometer on the cabinet of the VFD to adjust the flow. And they pull the flow from all the clarifiers that we have online through that header, that pipe in the back of the system up about ground level there, and then it pumps it back into trains 3 and 4. It's a single pipe goes over there, and then it branches off to the 2 trains. The 2 smaller pumps over there, these are WAS pumps, and we only have the ability to waste RAS at this plant, and those are the 2 pumps that do it. And if we'll walk over here, I'll show you where they pull off the header. You can see that the WAS pump's right there, and then over there where it says RAS, just to the right of that, you see that pipe right there? That is where we pull off RAS to be pumped out of the system. And the reason we're doing that is we want to maintain a specific SRT and specific mixed liquor concentrations, and using lab data we can look at that, determine what our SRT is, what our mixed liquor concentrations are, and then increase or decrease the amount of bugs that we're removing from the system to maintain those values. And those are the pumps that we use to do it. They run from the SCADA system, or they can run in auto and remote, which is totally through the SCADA system. If there's a problem with the SCADA system, you can also go in the Power Center 2 over there and run these from a VFD and control the wasting rate from there. Typically, we're only going to run 1 WAS pump, and you can see it over there turning very, very slowly right now. This structure here has sump pumps in it. It has alarms over there in the corner, which if you had a flooding condition here, they will send a priority 1 alarm. There's a klaxon will go off. That beacon on top of it will light. That particular cabinet and sump pump configuration is used throughout the plant. There will be 2 sump pumps in the sump over there. They'll run in hand or auto, and they're controlled by float switches, and there will be an alarm for high level and high level. As the level in the sump increases, it'll turn on first the lead pump. Then if the level keeps increasing, it'll turn on the lag pump, and at that time it's going to sound a klaxon, set off that beacon right there, and it's also going to signal a SCADA system that you have a high level in this particular sump. And if it's after hours, it's going to also it'll send a priority 1 alarm out to one of our pagers. And it's really important to respond to those, because if you get a high level in that sump, it could be, it may be just a hose running, or it could be the station flooding out. Maybe we've broken a pipe or something like that. So it's really important to follow up on a high sump alarm. And if throughout the day or on your rounds or whatever, you'd want to check to make sure those pumps are pumping. Things you want to look at are vibration. This is the RAS pumps themselves. You'd want to check on the motor, just check it for heat, vibration, just anything unusual. You want to check the output pressure on it, make sure that that's up to the set points. Right there you have a coupling that underneath the yellow enclosure, there's a coupling between the motor and the pump. And if you look closely, you can see that there's that spinning. It's like a rubber connector right there. And that's where the motor joins up to the pump. So, and inside there is that joint. And also you'll have a little bit of utility water being fed into those bearings there. But those enclosures are safety, there for safety. If you walked up and put your hand on one of those as it's turning, you could get hurt. And that insulated piping around there, that is utility water that's being fed to the bearings. If you lose utility water on a RAS pump, it will shut the pump down, and that's what that piping is doing there. It's feeding utility water to the bearings, and some of the sensors on there are also picking up on the water flow to the bearings. Those gray cabinets alongside the RAS pumps down there, those are local indicators for flow rates, and they also send totalizer information over to the SCADA system so you can determine how many gallons per day we actually pump from a particular clarifier. And also when you walk up and you're doing your rounds, you can look and see what the instantaneous flow is on the RAS pump. If we ever have to chlorinate the secondary system, that piping right there, the yellow piping running along the wall back there and feeding into the RAS pump, that's where that chemical is introduced to the secondary system right there. To collect a RAS sample, it's done right there by that sump. You can see that pipe down below there. And that sample is pulled from that main RAS line with the arrow pointing at the floor. If you see just above the yellow pipe there, you see that other brown tan pipe attached to the wall right there? That's where the sample is pulled from. What we're doing right here is we're scalping off mixed liquor, which would be going to the secondary system, but we're taking a portion of that mixed liquor and then using these pumps to pump it up here, and then it's going to exit right over here. So what we're doing is taking a large portion of mixed liquor and returning it to the head of the aeration basins, where it's going to be introduced with the primary effluent. Basically, it's going to make another trek through the aeration basins. And the pumps that do that are called mixed liquor return pumps. This is the E-stop for the MLR pump, MLR for short, mixed liquor return pump. You can turn these off and on from the SCADA system when they're in remote, or if they're in local, you'll have to go to Power Center 2 to turn them off and on. Typically, we like to leave them in remote. That way you can turn them off and on from the computer system. Under normal circumstances, they'll always be on. In a power failure, like if we switch over to generator, they will fail, and it's real important to start them back up. I think one of the things about the MLR pumps that's important is in a power failure, there's so many things going on that these can be overlooked because they're not readily visible and all that thing. So I think it's important to remember in a power failure, remember to check the MLR pumps. And there's displays that will show you the status of this. There's one for aeration basin 4 where I'm standing, and then there's another one, same spot on train 3. Right now we're standing in the center of our 4 secondary clarifiers. That's 3A, 3B, 4A behind you, and 4B. Again, the numbering over here is a little unusual because the expansion will be clarifiers 1 and 2. So these are the secondary clarifiers. The flow is exiting the aeration basins through the RAS pump station, and then here we are at the secondary clarifiers. Right now we have 2 secondaries online. We're flowing about 10 MGD per day, so we've determined that that's adequate. This structure right here is the scum removal system. So the secondary clarifiers have what they call ducking skimmers on them, and what they do is they remove any floatables from the surface of the secondary clarifier, and then by gravity they flow into this tank right here, and then this tank's controlled by, the pumps are controlled by level, and when we hit high level, the pumps will come on and they pump this to RP2. It's really important to periodically check it because the solids will sit in this tank and they can become very thick, and sometimes these pumps will not pump it. So it's important to take a look at that. And if you find that you can't pump from this tank to reestablish pumping, the best thing to do is open up the top, the panels on the top, and then begin flushing with water. If you're coming over here and you get an alarm on the SCADA system and it's high scum well level in this tank, you'd come over here and make sure that one of the first you could check and make sure that see how that check valve is open right there? So if you had a high scum well level, you should see that this pump is on, and either one pump or two pumps are on, and you can tell the pump is on. You can see from that float that it's on. So you want to check and make sure that this is an auto. If under normal circumstances, they should be in auto. If it's in auto but the pump isn't pumping, you can check for power, put it into hand, manually start it. You should see the check valve come up. If it doesn't come up, a couple things could have happened. One, there may not be power to this panel right here. There's several alarms that you have over temp on the seal alarms could be lit. Another thing that's happened fairly often here is there's some floats inside here, and when the solids are really heavy in this tank, they can keep the float from floating. So you'll have a high level alarm, which is this guy right here. You'll come out here and you'll see that this is lit, and you'll say, well, I've got a high level alarm and the pump isn't pumping. It's probably the float is probably either wrapped around something, or the solids are so thick that it can't float and start the pump. If that's the case on this particular pumping system, a lot of plants, you can put it into hand, hit start, and it will run. This won't do that. In order for this pump to start, even in manual, that float has to be free. It can't, if that float is not, if it's hung up on something, this pump will not start even in manual. So the best thing to do is open up some hatches up there, hose the area around down by the float. We also have we have like a 2x2 up there, and the reason that's up there is so you can reach down and jostle the float. If it's stuck on something or it's wrapped around a pipe or whatever, you can reach in there and kind of free it up. But the way you'll know that you've got a problem with this tank is high level alarm on the SCADA system, or if you're up here on the secondary clarifier and you see a lot of skimmings on the top, or a lot of foam on the top of the tank, you'll know that there's a problem there too. This is the north side of the flocculation tank here at RP5, and we have the ability to put polymer into the flock tank. We can put alum into the flock tank, or we can actually bleach it. Our permit requires us to use a token dose of alum, so that's what this line is doing right here. We're adding a very, very small amount of alum to the filters. We haven't had to use polymer at all, but if we did, this would be the line that we would use. And you have several points to bleach the filters, or pre-chlorinate before filtration, and these would be the lines you'd use for that. We've never had to do that here. The turbidity coming off the secondary system is usually less than 1 NTU, probably around most of the time I see about 0.5 NTU coming out. So we've had real great luck. So we haven't had to do anything extreme with chemical addition. These are the backwash water pumps for the filters. They're continuously backwashing, so each of the online filters is discharging its backwash water into a network of piping, which drops flow into this channel behind me. I want to say it's about 20 feet deep, and then these pumps are picking up the backwash water and returning it to the head of the plant. There should always be at least one of these running. As you're looking at it, you can see this check valve. This one's online. This is a pressure indicator on the of what the pump's discharging. Some of the things you want to watch for is if you get an alarm on the SCADA system and it says high high recycle water wet well, that is indicating that one of these pumps is either not adequate and another one needs to be placed online, or they have malfunctioned and one of them has failed. You'll get several alarms. If one of these fails on high motor, high amps or high temp or whatever, you'll get an alarm for that. But typically what we'll see is a high recycle wet well level alarm. And the problem that we've had here is the backwash water contains a little bit of sand in it from the filters, and at times the sand will pile up around the intake of these pumps, and you'll have to pull one out, and you may find that there's a lot of sand caught up in the impeller. There's 3 of them. Usually we're running 2 of them should do the job. This is the local indicator here. You can see there's 2 of them online. We're pumping about just under 700 gallons per minute. And in fact, right now, because of the high flow we have 3 of them online right now. This totalizer, this is an instantaneous read here, and then the totalizer is sent down to the control room, and we take that reading every day to keep an eye on our backwash water flows. That's what that's doing. The flow leaves a secondary clarifier through a common pipeline which enters the flock tank through that gate valve up there on the very top. You can see it, that rising, the awl that's rising up right there. The flow enters the flock tank right there through these flock mixers where it's continuously running, and we're adding alum in there, and that is causing it to flock, the particles to flock together. I'll pop the hatch on one of these. Right here behind us is a filter, and there's 4 legs coming off the filter. Each one of the legs has 6 modules. So when you're opening one of these valves up here, you're applying flow to 6 modules. So there's 12 modules. There's basically, the way the terminology works, there's 3 filters with 4 legs and 6 modules per leg. I've talked to a lot of people about these filters, and each person will call it something different, but generally everyone agrees on the term module. Things you want to look for is on this air pressure gauge right here. You're looking at about 10 psi right here on the flow. I'm sorry, it'd be about 10 psi on pressure, and the flow at 100. See that? Air to the filters is fed through these valves. So if you ever put one online, you want to make sure that this valve is open and you've got airflow to the filters, because they utilize an airlift pump. And sometimes when they're offline, we'll go ahead and shut the air off to them. And let me see, one of these, I'll open one of these up. What we're doing is we're taking our secondary effluent flow after we run it through the flocculators, which is we add alum to it, mix it in there, then we bring it over here and run it through a filter. And these are Dynasand filters, continuously backwashing. And what it is, the flow is coming up from beneath the filter media, the sand that you see, and then the water of the surface surrounding this circle right here is the effluent from the filter. The backwash water is the water you're seeing flowing over that little weir plate right there. And what's happening is as the water passes through the sand media, dirt becomes trapped on the sand. Well, to backwash it, you have an airlift pump right in the center of this, and the airlift pump is pulling the sand up through the center of this pipe, and it's agitating it. It's, the air bubbles are shaking the organics loose from the sand, and then that water is floating up here and flowing over the weir, the dirty water that we just created from shaking the organics off the sand flows through that, over that weir, through a trough, and then it's returned to the head end of the plant, and that's the backwash water. And if you want, I'll go look at another filter and I'll show you what it should look like when you pull it out. See, what we're looking for when we look at these filters is you see the backwash water that it's flowing, and then this is sand, and what we're doing here, you can see the sand is being pumped up through that center tube, and as the sand is picked up by the airlift pump, it goes up through this it looks like an electrical insulator. It's got little baffles on it, and it sets up some motion in the water to where it'll shake anything that's trapped on the sand off. And this is the sand that we're looking at. So that's what the filter looks like. If you ever want to service one or pull it off, there's an air line. You just disconnect this this right here, and you can pull the whole airlift pump unit off. So we've had real good luck with this. We thought they'd be plugged up all the time, and it hasn't happened. That center tube, there's one of them laying right over here. And the sand, which is the filter media, is picked up right through the bottom of this tube, and then it's pumped up all the way to the top. And when it reaches the top, it goes through this insulator structure that sets up kind of a motion in the water, which will shake, cause the sand to kind of shake and release any debris that's on the sand. And then the sand flows over the top of this and then back down, and then it drops back onto the surface of the filter. And here's the air line to it. I think the big thing to watch for, if you come by, sometimes sand will become impacted in the end of that tube, and if you shake it, raise it up like I did to show you that filter, shake it a little bit, see if you can loosen the sand up. That's one thing you can do, or you can pull the whole tube out like we did right here and take a look at that. The biggest problem I've seen where it really is a problem is if you have plastic debris covering the end of this tube. If this gets plugged up, it'll cause the filter to fail. So if you see debris in the secondary clarifiers, like a plastic bag or trash or whatever, if you can get it while it's easy to get, it'll save you a lot of problems, because otherwise it's going to probably end up in the filters and probably get sucked into one of these, and we'll have to pull it out and clean it. The bottom of the tank, the bottom of the filter has a cone. So the sand is constantly falling into this cone. So when you raise this up high, the sand is falling. So when you drop this rod back into the sand, since the sand's falling, it's going to want to fall with it too. There's a circular tube though that this thing will fit into. And so it's important that when you put this back, it'll just drop right in. Well, let me pull one out. I'll show you. You can tell by just looking at them. Some of them are. If they have a lot of debris on top or something like that, that's probably that it needs to be looked at. But what'll happen? See, I'm going to bust it. I'll pull this one out, and see the sand's coming up. So that's the backwashing. The mucky, that dirty sand is being cleaned. But see how it wants to fall all by itself. See that? I'm just dropping it, and then the sand is being pumped up the tube, so it wants to drop all by itself. So I'm just kind of helping it. But when it gets to right in here, you want to make sure that that is sitting in the tube properly. That's good. But that's the only thing, it will drop all by itself just like it did right there. But when it gets to the bottom, it sits in a cylinder, and you want to make sure that that barrel fell right in that cylinder. Because if it's sitting on top, it won't pump sand, which when it's not pumping sand, it's not filtering. So to answer your question, they pretty much go in all by themselves. Right now what we're doing is we're going through the process. We can't control these by the Foxborough. There's a problem with the electrical system out here. There's noise on the line. So what we have to do when we put them off and on is to open and close the valves by hand. That's probably the best way to do it. You can do it electrically from one of the power centers, but you want to have somebody with you to make sure that when the valve is open or closed, then throw the breaker. If you leave the breaker on, this valve could open or close on its own, all by itself. Another thing you want to watch for too is we have to look at the flow, where our permit requires us to maintain 5 gallons per minute per square foot or less on the surface of the filters. So you want to make sure that you have enough filters online to cover the flow that you're treating. Plus, if there is a fluctuation and a lot more flow does come in, you got enough filters online to cover that additional flow.
How do you know you are?
It's on the screen, on the RP5 effluent screen. It's calculated for us, and I'll show you on that screen. And we have alarms too. If you exceed the filter loading rate, you'll get alarms for that. But usually we run about 12 filters, which is enough to cover far more flow than we'll ever see. Like the rating for this filter system is like 27 MGD, and we're only at 10, so we're in pretty good shape.
When you say 12 filters, are you talking about 12 of these arms?
12, yeah, 12 or 12 modules are on. Which is, this is like 1, 2, 3. Like this valve would be open, we'll call that 1. And then 2, 3, 4, 5, 6, 7. Yeah, I think we might probably have about 9 on. I'd have to look right now. But yeah, you'd have to have 9 of these valves open to make sure that. That's where we really probably need to standardize on the terminology, because depending on who you're talking to, because if you talk to the builders, they'll say that we have 3 filters. And some people will say, well, we have 12 filters, which is counting all the arms. So I don't know, maybe for training, we should come up with some kind of a standard.
So there's 6 on each one of these modules?
Yeah, 3 filters, and then you have this these 4 distribution points, and then 6 modules. And a module is where I pulled up that filter, that airlift pump. That would be like 1 module. This right here is the discharge points for the filters are right here. They're going to flow into this channel, and then from this channel they'll flow into the chlorine contact tank over there. If you want to bypass the filters, you can close that valve up there, on that gate valve up there. You would close that, and you would open this, and the flow will then go around the filters and straight to the contact tank. You'd never want to do that unless you consulted with a lot of people, because bypassing the filters is a violation of our permit. So if we're discharging, you're out of compliance for Title 22. We've suggested for a capital project to have this bypass to that lagoon over there. It's not happening yet, but that's what we want to suggest. But yeah, if somebody ever came up with an idea and they said we need to bypass the filters, that's how you would do it. These tubes are attached to the discharge of this pipe, which is the secondary effluent coming, or from the flock tank. There's a ping pong ball on the top that floats on top of the water that's in this pipe. So this pipe is connected up to where it'll give you an indication of the water level. in the filter. And in theory, the ping pong ball floats up here and it tells you this filter's plugged up. The problem with that is if you ever have the filter plugged up that badly to where you can see that ping pong ball, you have a very, very significant problem. We had talked about stacking some additional floats or modifying this in some way to where you could see the ping pong ball and then put a marker on here, you know, to tell you that you have a problem with the filters. But over time we've determined that that's just not a problem. There's so many other things that you would see before you saw the ball float to the top of that pipe that we just kind of left it alone. These are Ingersoll Rand air compressors, and these are the air compressors we use for the to run air to the filters, the tertiary filters, and they also provide air to the pneumatic valves on the aeration basin. So it's really important if you have a problem here in the plant, particularly a power outage. Some of the first thing you want to do is come in here, start the blower, and then come by here and start this air compressor. If you start a blower up and this air compressor isn't running, the pneumatic valves up on the aeration basin, they won't open. The blower will still run, but you won't be pumping any air out there. Also, you won't have the ability to run the filters either. To stop it, it's just this button right here. It's a very simple unit to run. That would stop it. If you came in here for some reason and you wanted to, you know, it was smoking or vibration or something like that, this is an e-stop. It's all self-contained. The mechanics open it up. There's air filters and things like that in there, but they do all the servicing on it. There's two of them. During a power outage, they won't start. You have to start it yourself. I think what else there is to these. It's pretty simple. This is the air drying unit. The equipment out here requires, you know, very dry air because so what it's doing right here is pulling the water out of the air that we're sending to the pneumatic valves and to the filters. And that's what this is doing right here. This is a coalescing filter, and it's removing impurities from the air that we're pumping to the pneumatic valves and to the filters. And this is something the mechanic could probably tell you more about how it works. But basically, what this is doing is making sure that we have clean, dry air being fed to the plant system, the filters and pneumatic valves. So this is a contact tank, and the flow comes off the filters through a pipeline and comes in this vault right here that I'm standing on. We add bleach to the influent of the contact tank through this line right here. And this pipeline right here, this is a bleach line that feeds bleach to the water champ, which is a mixture that we're using. Right now it's out of the water. We've been testing it, and I believe it has an electrical problem right now, but this is the water champ that we've been using. The bleach will flow through this pipeline right here, inject it into the water champ, and then this little propeller, which spins real quickly, spins it into the water, or disperses it into the water. It's a low horsepower engine, and it's supposed to be really efficient. We just had some problems electrically with it, but that's the water champ. This is a Philadelphia mixer right here. It's a big mechanical mixer, and when we're not using the water champ, we'll use this Philadelphia mixer. You can turn this off and on from the Foxborough. It's got icons on the contact tank that'll tell you the status of this motor. If you lose this mixer, one of the signs you'll see of it is the influent residuals will change. When you lose mixing here at RP5, you'll have a high residual on one analyzer and a low residual on another analyzer. And that's usually the first indicator that you've got a problem with mixing. So if you come out here, you run your residuals and everything looks okay, but yet you have an imbalance. The residual over here is like 10 and the residual over on the east side is 5, I would check the mixer. The Philadelphia mixer is pretty obvious. If it's running, you're going to know it because you can hear it and feel it. The water champ, there's no indicators on this that it's not working. If it fails, what'll happen is you're going to have some high residual in one side of the tank and a low residual on the other side of the tank. Instrumentation, they'll check it out and they're going to say, hey, the analyzers are right on. So what that tells me right away is the water champ has failed. Getting this in and out of this tank involves opening this hatch right here and then dropping it with this little crane into the water. It's wired in such a way through this switch that you cannot start. You have to turn this Philadelphia mixer off to start the water champ. And the reason is they share the same vault. And if you have the water champ in this vault and you turn this on, the control cables, the power, the water champ itself can be drug into this impeller. So what our electricians did was wired in such a way that if you do drop the water champ, this has to be switched off. And it's done through this panel right here. After we inject the bleach right here in this vault, either the water champ or the Philadelphia mixer, they'll mix the bleach into solution, and then it's going to come through here, down these channels, and it's going to enter the contact tank. And these are the influent residual analyzers. And what it's doing is it's measuring the chlorine residual to the front end of the contact tank. And right now you can see it, we're running at 10 right here. It's got a small peristaltic pump. One of the things you'll find is that we have 2 residual analyzers, and it's nice because the redundancy allows you to have a problem with this, and then one of the analyzers, and through the SCADA system you can switch to the other analyzer. It's very seldom that both analyzers will fail at the same time. One of the things that'll happen is you'll get little air bubbles in these tubes right here. And then that air ends up into the analyzer system and it will throw off your residual. So sometimes if you come out here and you think, gosh, I checked my bleach pump, I know I've got all good set points, the pump is pumping properly and all that, but the residual is really low, I would check for air in this line.
How would you see it?
You'll just see little tiny air bubbles in here. You just push them out, you can squeeze the tube like that, and you just help the air bubble pass through that peristaltic pump. To help with it, you have this little chimney right here, this little standpipe, and the idea behind that was to release the air. You know, you're pulling your sample out, and hopefully the air will pass through here and end up going just out of this pipe. But yeah, that's what you would do. You'd see little air bubbles here, and you try and help them out, you know, by pinching this tube. And then that's something you could do at night. During the daytime, if you have a problem with an analyzer, the best person to look at it's an instrument tech. You can try a few things yourself and help the instrumentation people out by doing that. But if you're not sure, or if that fails, you would go get an instrument tech. But we have 2 analyzers on the influent side and 2 analyzers on the effluent side of the plant. And they're pretty important. Right here, this is where the sample is pulled up. You have east and west analyzers. This sample pump right here, if you were to have a problem with an analyzer, you could check this pump, make sure that it's pumping. And you'll know right away if it's not, because this flow would stop if I shut off that pump. So when you walk up, you can generally tell. As long as you have sample going up there, then you can look in here and trying to, you know, look and see if you have air in the lines or not. But this is where we inject the bleach right here. It's going to flow down this channel that I'm walking on, and it's going to come down to that end of the contact tank, and then it goes through a serpentine. And we figure the detention time on here at our current flows is about 4 hours. So it's going to serpentine through this tank, and then it's going to exit the chamber out on the south end down there, where we measure it for chlorine residual again. They have effluent analyzers, an east and west effluent analyzer. So on this side of the tank, we have, this is the south end of the tank, this is the effluent analyzers. The flow exits a tank through this gate valve right here. It's going to analyzer, it's identical to the influent. Same configuration right there. And you have the east and the west. What's nice about the system is if this analyzer were to fail, you can control the plant off of that analyzer or vice versa. And you can do that. You can log in if you're on call and it's the middle of the night or what have you, and suddenly your effluent residual goes very low. One of the first things I would do from the laptop is switch analyzers. And you'll be able to tell too, like if this is reading like 0 and you've got a residual of 5 over here, what I would do is switch on to this analyzer and see, check out what happens after that. We do titrations during the daytime to verify that the analyzers are running correctly. What you want to watch for though is the analyzers control, that signal is fed into the plant's effluent flow times this residual, and it computes the SBS. So what will happen is if you lose an analyzer and this goes to 0, it's going to tell the sodium bisulfite or dechlorination system you don't have any residual, so there's no need for sodium bisulfite, which is going to begin decreasing the sodium bisulfite. The next thing that's going to happen is the flow from the tank is going to come over here. It's going to be picked up by a pump sent to that small building over there, and the Z-chlor, which is measuring for chlorine residual, which basically it's checking for a chlorine residual. If it sees a chlorine residual after a minute, it's going to shut that gate over there, which is a final effluent diversion gate. So it's really important to respond to an effluent chlorine residual analyzer problem. If it's either going low, basically it's going to tell the system we don't have a residual. It's going to ramp the SBS down, sodium bisulfite, and trigger a gate closure. So if you're on call at night, you can log in with a laptop, switch analyzers. If you switch analyzers though, and you still have, if you do have a problem with it, let's say you switch over from one analyzer east to the west, and the west isn't working, even though you've switched it on, it's still not working, the gate will still close because the Z-chlor will see it and it will tell you that it's going to signal it and say, hey, we've got chlorine out here, which is a discharge violation. It's going to shut the gate anyway. So there's a couple fail safes. But so during the night, you don't have to worry about, gee, I put on another analyzer and it was malfunctioning. You went from an analyzer was out of service to a malfunctioning analyzer. The Z-chlor will still catch that, and it'll still shut the gate. I'll show you the gate, which is right over here. This is the gate I'm talking about right here. When this gate closes, right now this pipeline that this gate is located on goes to Chino Creek, which is out across the way there. When this gate closes, it's going to fill up the contact tank and overflow this wall right here, and then it's going to travel down that pipeline to that earthen lagoon over there. So we're going to pull our final effluent. It's going to end up in that lagoon over there, and we try and keep it pumped down, so there's plenty of capacity over there. The downside of that is if it's during the rainy season or something like that, that's also our stormwater lagoon. So we want to try and keep this as low as we can, and to do that, keeping the plant online, minimizing the number of times the gate closes are really important. But to answer your question, when the gate closes, it'll overflow into that pipeline to that earthen lagoon. And restarting the plant is something you really want to understand everything going on when you restart the facility, and we'll go through that on the SCADA system. What you're looking at right there, that gate valve right there, that allows us to feed chlorinated water to the utility water system or dechlorinated water to the utility water system. By opening and closing it, you're basically supplying it. When it's open, you're getting dechlor. When we close it, it's chlorinated. So this orange pipe coming up the wall, this is the sodium bisulfite line, and it's coming up to this is the line that provides sodium bisulfite for dechlorinating the effluent. It's important, this is a backflow device right here, and it puts back pressure on the system to where the pumps, we have a problem here because the pumps are located very far away, so the response time was rather low. So by putting this backflow device on it, it puts back pressure on the pump so that the line between here where we discharge and where the pumps are located is constantly pressurized, and so when a gallon goes in, a gallon comes out the other side. But what can happen is this can become plugged up, and if it does get plugged up, you'll see this dial indicator peg out. You know, it'll go up, it reads to 60, it'll be at 60, and what that's telling you is we have 60 pounds of back pressure on the system. The pumps can't overcome it, so they're going to be having to work really, really hard. What'll happen, something you'll see is if you have an alarm and you're not dechlorinating properly or something, this would be one of the first things I would check, is check this pressure right here. It should be about 5 psi or so. If it's running at 60, this is plugged, and one of the things you can do real quickly is get a wrench and run the back pressure of this knob all the way in and all the way out to, if there is some kind of buildup. You can see where we've had a little bit of leakage here. This crystallization may be on the inside of the valve or the inside of the back pressure valve. So by opening and closing this, you can kind of work the crystallization out of the line. It's heat taped to keep it from crystallizing, but it can still happen. This is really important that if somebody wants to service this, this is the only, we're dechlorinating from this, so to service this back pressure device or work on this pipeline at all, you would have to dechlorinate the plant's effluent from this other line over here. And this line here is connected directly to pump number 2. So you would have to dechlorinate using pump number 2 through this pipeline over here. And you can see this has a back pressure device on it also. It's not heat taped. The thing you'd have to be aware of though, if you're dechlorinating the plant's effluent from here using pump number 2, you're working with very little safety. There's no other way to dechlorinate the effluent after this. If this pump were to fail or that it's not set properly or something like that, you're not going to dechlorinate the effluent and you're going to discharge a chlorinated effluent. So it's really important, if they have to service that dechlorination point down there, it's really, really important to keep a very, very close eye on this. We can set the gate up to close on a positive chlorine residual seen at the outfall Z-chlor. The thing is it's going to go positive on the outfall Z-chlor, but the gate takes 6 minutes to close. Our limit is 5. So we're probably going to have a violation if you're on this dechlorination system and you have a problem with it. Even though the gate's going to close, it's not going to be fast enough. One of the things I'm looking at doing is running that gate halfway down to where maybe if we had it positioned lower, that it would close quicker and maybe it could catch it before we had a problem. But again, that's something that when you have a situation like that where you're dechlorinating with just on the back end of the tank, you really want to watch that very, very closely. And you're best off, depending on, you want to really talk it over with everybody, and probably you're better off shutting that gate, bypassing your flow to the lagoon and dealing with the problem. But if for some reason the lagoon were full or something like that and you had to do it, that would be something you really want to watch very, very closely.